Everybody, it's Mr. Gustin. I'm back in the physics classroom. Today, we're talking about a new demo, an introduction to a new type of energy, a rotational energy, okay? We have talked about energy quite a bit. Now, we're at the point in our second semester unit of rotation that we've gotten through kinematics, we've gotten through torque, we've gotten through dynamics, and we're beginning to discuss energy. In our review lab for our kinematics and torque dynamics assessment, we introduced the idea, we came up with the idea that there is energy stored rotationally in an object that is rotating. So there's a different kind of kinetic energy than we've discussed in the past, and today we're going to break that down, okay? So it's Thursday, but it's kind of Friday for the students, so happy Friday. This is all these notes back here. I'll let you read those. Here's what I got for you today. All right, new demo. I've got a paper towel roll, and I'm going to go ahead and drop it from a height. Now, the height is marked over here. I already measured it out from class up here. This is 2 meters above the ground. That's what that is. I'm going to drop it, and it's going to hit the ground. And so we can watch that, but I'm going to hold one side of the roll and drop it like so, and it's going to fall 2 meters. All right? So if we went ahead and tried our, quote-unquote, first semester way of doing this, what we would probably do is start by drawing a picture of our object here initially at rest above the lowest point in the system, and then it's going to fall, and down here as it hits the ground, all of that UG will convert into kinetic energy, and so we'll see a conservation of energy expression that looks like this. UG equals K, mgh equals 1/2 mv squared, and we can solve that final velocity is equal to root 2 gh. If I go ahead and solve this, straight up, if I go ahead and solve this as a predicted value, what should my speed be at the bottom when this paper towel roll hits the ground? I can do that without actually dropping it and without taking any data other than height. If it's 2 meters and I drop it 2 meters, the velocity ends up being 6.26 meters per second. This is the predicted final velocity if this energy expression is true. If we drop it from 2 meters, the predicted value based on our energy expression here, we start with UG, it falls, it's moving, we get this conservation of energy expression, it simplifies over to this, the masses cancel out, and I'm left with 6.26 as the final velocity. I want you at home to predict this quantity. Determine what is the actual, can I get both in there? I'm going to back this table up, it's going to get loud. Well, it wasn't so bad. If I back this up, you can now see the 2 meters up there, and you can see the ground. So I'm going to jump up on this this ladder here and drop this roll of paper towels. When I do that at home, you should be timing. Let's time how long this paper towel roll takes to get to the ground. We'll use time and distance to end up predicting or calculating the actual speed at which the roll hits the ground. So we're up here. I'm going to drop it in 3, 2, 1, go. It hits the ground, it rolls. If you notice, as I hold it, there's a tension force in it. This is going to be a mess to roll back up. We'll see what I can do. I'll roll this up later. So take some time at home. I'm going to make up a time here in class that I think, based on some class data we took earlier, but in class, hopefully you got a couple times and you can take that time value and use it as an average. But in class, the time that we got, the average time after we took 30 trials from everyone in class, is 0.7 seconds. That's the average time that we got. So to calculate the final velocity, we can use our average velocity formula, where change in position over time, that's my average velocity, and average velocity is final plus initial over 2. Initial is 0. So I end up with 2 times change in x over time, that's final velocity. And what it ends up being is 2 times 2 over over 0.7, so 0.7 times 4, 4 divided by 0.7. I end up with 5.7 as a final velocity value. Actually, 5.7 meters per second is what I have. This is my final velocity. Not what I predicted, it's what I have based on what happened. My predicted is 6.2, my actual is 5.7. And we say to ourselves, well, those aren't close, right? They're small numbers, so small differences mean, small value differences mean larger percentage differences. So these aren't close, and we've forgotten something. And this, hopefully you're seeing, like Gustin, you forgot about rotational energy, and you're absolutely right. Let's go ahead and take a peek at what our rotational energy equation is. If we go back to the theme that we have kinetic, we can call it translation for linear, and we have kinetic rotational energy, we know that this kinetic energy is equal to 1/2 mv squared. We always are looking for the complement, the synonym, the equivalent for rotation to linear. So my rotational equation must look very similar. But we don't use mass alone when we're talking about how things rotate. We use inertia. We use the moment of inertia, or rotational inertia I. That's the synonym for mass in rotation. We don't use V when we're talking about rotational energy. We use omega. And so we end up with this equation right here, that kinetic rotational energy is equal to 1/2 I omega squared, and it's on your equation sheet in the bottom left of that equation sheet. It's there for you. You can go find it. Here is your task. Here is your task to finish this little introduction. Your task is to now add K rotation to your energy expression and then solve for this final velocity. How will we do it? We'll need to do it using I, and so we'll need to know what the radii are of this. Okay? There are two radii. We have the radius inner and the radius outer. The inner radius is 2.5 centimeters, and the outer radius is 4.25 centimeters. The I for the roll is equal to 1/2 m r outside squared plus r inside squared. Does mass matter? I mean, there's mass here, mass there, mass there. That's going to cancel out. I don't necessarily know omega, but I do know what the linear speed is as it moves down. All right, I'm solving for linear speed, right? I want to find v, and v shows up in both. I can replace omega with v over r using a bridge equation. So your task now is to go ahead and find velocity and see how much closer it is to 6.26. This is kind of our little in-class proof that when things rotate, kinetic energy is stored in that type of motion, and we require that type of motion to have more accurate explanations mathematically, verbally, graphically, when we are dropping things that are also rotating. Okay? If you got questions, drop in the comments, send me an email, ask me in class. Until next time, see ya!